Okay. Okay. So today's topic is whatever is written there. Dynamically linked structures using self-referencing pointers. Okay, so whatever complicated it may sound, it essentially has to do with our final application of pointers. Uh, in the last class, or maybe in the last two classes, we have used pointers to point to.
Excuse me, sir. Are you sharing your screen, sir?
Yeah, I'm sharing screen.
Sir, it is not visible to me.
I don't know. Is it
It is
visible?
visible actually. Yes, yes, sir. It is visible.
Yeah. Maybe you wait for some time. It will come. Okay. So use pointers to point to.
Yes, sir. Yes, sir. Now it is visible, sir.
Okay, fine. So use pointers to point to dynamically
Wings medals in them.
allocated arrays. Things like this. Maybe array of integers, characters, structures, whatever. And you have a pointer P allocated sufficient memory, and then you can call P0, P1, P2, and so on. Today we will see, we'll allocate, in a sense, single element arrays. So it will be something like this. It's a single element. Okay. But then, what is the use of such a single element array? The idea is this. This is typically a structure and it contains one or more pointers of the same type. Okay. So this pointer and this pointer, they are of the same type. Okay, I may have multiple such pointers, even an array of pointers inside the structure. The idea is that I will not allocate an array of such structures, but just memory, just the amount of memory sufficient to store a single structure, single record, which contains one pointer of the same type. Okay, at least. There may be multiple pointers, but for the rest of the course, we will mostly concentrate on structure with one pointer, because it is the same type. These are called self-referencing pointers. Okay, but this is the basic building block of what is called dynamically linked structures. Okay, as an application,
Sir,
yeah,
sir, there will be a pointer within that structure which will point to another type, like structure
of the same type.
Yeah, of the same type. That will be a self-referencing pointer, but there will be a head pointer, right, which points to the first structure.
Yeah. So you need some kind of head pointer, root pointer, or some, I would say, master reference.
Yes, sir. So do we call that a self-referencing pointer as well, or is it the structure pointer only?
The pointer is of the same type. So This pointer is self-referencing, so these are the same type, and therefore we call this type, not exactly this pointer, this type a self-referencing pointer. Okay, it's not exactly a pointer uh, being called self-referencing, but the type of the pointer being called self-referencing. But anyway, this is just a jugglery of the words. As an application, we will look at some kind of dynamic structure called linked lists. In fact, we will talk about singly linked list. Is a list where each node contains some data plus only one self-referencing pointer. Okay. So the question is, how do I define such a structure? Okay. So it's already, let us do it in conjunction with type def. I will give it a name. I keep some space open here. You may have type 1, data 1, or field 1, type 2, field 2, or data 2, and some amount of data you have. Maybe I just delete this for the moment. And some key data fields, data k. Then you have one or more self-referencing pointers. But how do I? What is the type of that? The structure is not yet fully defined. Therefore, whenever I use one or more self-referencing pointers inside a structure, I must give it a name. Maybe underscore node. So here I say struct underscore node, maybe link 1, link 2, blah blah blah, up to link some number of things like L. Okay, and then I define this, type this as node. Okay, so this is a situation where this tag is necessary, because without this you cannot reference this structure. Okay, so this is one important thing. This is necessary even if we are type defing this structure. Okay, so this keep in mind. So if I want to call it node, maybe I give underscore node or something like that. I cannot use node here. The reason is that this part is first parsed, I would say. Once the compiler knows what kind of data type or structure I am type defing, after this it will give a new name to this node. So this is important here. Although I am type defing this as node, I cannot use node. That is the type def name. Okay. In fact, I can completely forget this type def. I can simply say struct underscore node this and here semicolon. Okay. That is also fine. I am also type defing this. So after this,
So, link 1, link 2, these are supposed to be the pointers, right?
These are supposed. Sorry. Yes. I should say start. Yes. Thanks for pointing out. Yeah, these are all pointers. Yeah, start. Okay. Without start, this is not a valid thing. Sorry. These are pointers. So after this,
That's what.
struct node, and since I have typed depth struct node as node, I can use these two things interchangeably. Right. So this is the basic way of defining a structure with self-referencing pointers. The important things are this formal tag is necessary because this is what I use for defining these pointers. Okay. And I have this self-referencing things, pointers. So these are pointers. Yeah. So let me highlight. I just forgot. This is a pointer, this is a pointer, and so on. This is a pointer. Okay. Okay. So I will write a fairly big code today to illustrate how such linked lists work. Okay. Maybe I start with a sample struct stud. I am not type defing, but that is fine. Character name 100, character role 100, or maybe 10 is good enough. Float CGPA and int age. So this much we have already seen. Then I will have a self-referencing pointer. Let's call it next. Only one. Okay. So this is how I define a structure type.
It should be a pointer, no? Struts are
Okay.
next.
I'm making the same mistake again and again. So this is star next, not underscore next. Yeah, it's star next. Okay, so how does it look like? It is a structure of this form. It has a name array. It has a role array. It's a character array, so it comprises this. Then there is just a floating point value called CGPA. There is an integer age. Along with that, we have a self-referencing pointer, this. And this is called next. Okay. So we will see how I can link up several such structures in the form of a chain, a linear chain. So let us see. We usually do not do it this way, but we can have this. Okay, struct stud S1. Let us initialize it as, let's say, Abhijit. Roll number is whatever. CGPA is let's say 9.02 and age maybe 100. Okay. I have S2, maybe another student. 20 CS 9876. CGPA is let's say 8.56. Age is let's say 20. And I have let's say a third student is 3. Roll number maybe CGPA maybe, age maybe 27. Okay, so this way I create, okay, it has another field, right? It has, in addition to these things, I have one pointer. So I didn't initialize it. Of course, if I do not initialize it, it will be initialized to the null pointer. But anyway, I can explicitly do it. So it's preferable. Okay. Null, comma, null, comma, null, semicolon. Okay. So this creates 3 student records. Okay. And they look like this. Let us see. The first record is this. What was 998B 1331? Nine point something. Okay, 9.0200. Finally, I have a pointer which is null. So this is what I call S1. S2 is another thing. Hmm, 20 CS. What was the 9876? Okay. CGPA was 8.5620. And I initialize the pointer to null. And the third structure that I have is something like this. Its pointer is also null, S3. 18GG 12345. CGPA was 9.2327. 9.23, age is 27, and this is null. Okay, so maybe I add another pointer, another thing here. Okay, let it be just semicolon. And I will simply add a pointer star t. Initially, it is set to null. Okay, so let us have all these definitions. Then what I do, so t is currently a null pointer, where should I go? Okay, here. Okay, so t is somewhere pointing to null. And I have created this structure. So now if I say p equal to and s1, s1 dot next equal to and s2, s2 dot next equal to and s3, Then what will happen? I will use another color, maybe green. Then P will essentially point to this. And S1 next, this will point to S2. And S2 dot next, this will point to this. So now if I start from P, I can visit structure 1, S1, student 1. Then I follow the next pointer. I go to student 2. Then I follow the next pointer. I go to student 3. And then if I want to follow the next pointer, I hit now. So that means my list has ended. Okay. So this is what is called a linked list. Of, let's say, size 3. Okay. So from this description, you see that we will typically not use linked list this way. We will dynamically create it. But this is a structure that I can actually define. This is a kind of dynamical structure, dynamic structure that I can define. So one thing is that a linked list has a header. In this example, the pointer P, and some way to mark end of list. So in this example, this end of list marker is the next pointer is null. Okay. So there is actually another convention which we will not follow, but it's good to know it. There is another thing, another I would say another common technique to end a list. It is something like this. Instead of letting it point to nowhere, the null pointer, it may point to itself. Okay. This is another convention. So if you come here and when you follow the next pointer, if you are at the same, you would say, structure, okay, this pointer and this pointer, they are the same. Then also there is another way of, I would say, indicating that the list has ended. Next pointer points to the node, the last node itself. Okay, but in the rest of the discussion, we will follow this convention. It's interesting, it's important to know that this is another possibility. Okay, so this is another possibility. Another allowed possibility. Okay, but we will follow this. Okay, there may be other conventions, but anyway, these are the two most common ones. So this is fine, right? Okay.
Yes, sir.
So instead of creating and linking nodes in this fashion, as illustrated here, I will do something more natural. But before doing that, let us look at a traversal mechanism. Okay. So from now on, instead of using struct std kind of thing, I will just use simpler thing. Contains an integer data and a self-referencing pointer. And I call it node. I may also define type def a pointer to this node kind of structure. I may call it a header. Okay. So this pointer and this pointer, they are of the same type. Only thing is this is a standalone pointer, whereas this is a pointer that is a part of the structure called struct underscore node or node. Okay. Now, when I want to visit all the elements of a node, and maybe I just print the data. Okay, I will actually write the code, but let me for the moment write it here. So I will just write a procedure called void traverse, and here I will pass the header. Let us call it P. Okay, of course, instead of header, I can also use node star P, because header and node star, they are of the same type. I could have also used struct underscore node star P. Okay, so these are other possibilities. Anyway, so here what I will do, I will simply traverse. Okay, if I have to,
star P or
huh?
header star P.
No, header is already star. Yeah, I have defined it, right? It's already a pointer to node. Okay, so it's not header star P.
Okay.
Okay, either say node star P, struct underscore node star P, or just simply header P. Okay. So while P, which is saying that P not equal to null, null pointer returns 0 basically. Okay, so I was going to draw a picture. Sorry. So this is the header. I have 33 stored here. I have 59 stored here. Next one maybe 17. Next one maybe 25. And then I have now. So I supply this header pointer P, and I want to print the integers, the data field. Okay, this data field one by one as I encounter every node. Okay, so this traversal procedure goes like this. While P is not null, printf %d, maybe a new line. P is a pointer to a structure, so I can use this. P is a pointer, so it's either star P dot data, or I can simply use this. Okay, this is a situation where this notation makes, I would say, reasonable intuitive sense. Okay. Then I have to advance this pointer one step.
Anything you ask. So we will be like,
Huh? Is there any question? Okay. So then I say P equal to P next. Do some work here. For example, here I am printing, and then this is the advanced mechanism. It is important to note that it is not P++.
So means in linked list the nodes can be anywhere on the register. They need not be contiguous.
Yes. P++ may work if it just happens that these are on two contiguous memory locations. So it is important to note that in general P++ it will not work. Okay, so that is what I wanted to highlight. It is not P++. You have to advance using this construct. P becomes P next. Okay. And eventually P becomes null when the end of list is reached under the convention that the list ends with a null pointer. Okay. So if we follow the second convention, I leave it to you. How do you check? Okay. In fact, it's actually, anyway, you check. Okay. So P equal to P next. That's it. That is the traversal mechanism. Do some work. Okay. Let P point to the next pointer. Okay. And P is a node pointer or struct underscore node pointer, or I simply call it header. If I have type def node star or struct underscore node star as header. Okay. So you see that I am actually changing this pointer P. Okay. Which is supposed to be header. Okay. So we are changing P. And from the main, maybe I am calling traverse something like H. H is the header pointer. Okay. So what will happen to H? Now P becomes P next, P becomes P next, P becomes P next. Eventually P becomes null. But if I call it with from main like traverse H, what
Sir,
will
H
happen
will
to H?
remain same because it
Huh?
is a P is a copy of H. H will remain same.
Yes. So you see, it is always pass or call by value, call by copy. So this P is a copy of that pointer H. Therefore, whatever change we make to P, this is not visible to H. Okay. Okay. So this is the traversal mechanism. And this is the crucial point. You do not use P++, use P equal to P next. Okay. And while P, this also makes sense. You can also write it as while P is not equal to null, only the null pointer will return 0 and will allow the loop to break. Okay.
Sir, one question.
Ah.
Sir, you just like briefly discussed that another method of ending the linked list. What would we have written if like that method were used?
What?
Like if the self-referencing, like self-linking method was used, like in the last, the next links to itself. So what would we have written in P to end the traversal?
While P not equal to P next, something like that.
Achha, okay.
Right. Something like that, right? So if we have this
That's all.
convention, where is it? If we have this convention, when P comes here, P next will also lead you to the same node. So P and P next, they are essentially the same pointer. I mean, 2 copies of the same address.
Yeah.
Also, you use it after you print this value. So all the change is that after you print whatever is written there. So you do these things. Henceforth, we will follow this null pointer termination convention. Okay.
Okay, sir. I was just curious to know.
Yeah, no, that's fine. That's fine. Okay. Okay.
Sir,
Tell.
sir, if we do P is equal to P next, then you said that there will be no change in the pointer in main. Means, sir, if we pass a pointer to a function, then that is passing by value. This means only the address is passed. So I did not understand that thing. Means how it is happening.
No. What I mentioned is this. This is a function. Okay. Okay. So I have a main like this. Well, you have that struct declaration globally, and here I have header or node star or struct node star list head, and I will mention in the rest of today's class build a list, how to do it, headed by L. Okay, we will see how we can build lists using dynamic memory allocation. Okay, of course you have seen one thing, something like this: p equal to and s1 next equal to and s2 next equal to and s3 and s3 next is null. This is one way of doing it, but we will see a more dynamic way of doing it. Then when I say traverse this list L, then I will call this, and here you see that P is changing to P next, then once again P next, and once again P next. Eventually this loop terminates when P becomes null. So eventually at the end of this loop, P becomes null. So that does not mean I have lost track of this list L. So the idea is that in the function, P becomes eventually null. Okay, but P is a copy of L, so the two things together imply that nothing happens to L as a pointer. So that is what I wanted to mention. So L continues to store a pointer to the first node of the list. That address is copied to P, and then that P is changed, so nothing happens to L. So this is what I meant. Is that clear now?
Okay, sir.
Okay.
Understood.
Okay, fine.
Yes, sir. Sir, it should be headed.
Huh? There was another question. Okay. Maybe, I don't know.
Sir, if we want to make changes in a header L, means in L, then how can we do that, sir?
Yeah, we'll see how we can actually, let's say, grow or shrink a linked list inside.
And
We will see. That is what the rest of today's class is there. So what I have already demonstrated
Sir,
is,
if we change L, then the like the beginning of the linked list will be lost because there is no back link to the previous node.
exactly. Yes, it is lost.
But that can be used for deletion from the beginning algorithms, right?
Yeah, we will see this insert, delete, all these things. We will start things today.
Yeah, I wasn't referring to delete.
Yeah. Yeah. So how do you delete? And how can a function change a linked list? So these are the things that we will see.
Excuse me, sir.
Tell.
Sir, why is this header star L? Shouldn't it be header L? Because header is already node
Yes,
star.
yes, my mistake. Either say node star L or just header L. Yeah, yeah.
Yes.
Mistake. Yeah. Either header L or node star L or struct underscore node star L. Yeah. Okay, header star L also makes sense,
So
but
if we make it, so if we make star L, then we can modify the L if we pass star
L is a pointer, right? L is
Yes,
a
a
pointer.
star L would be a pointer to a pointer. So I think we can change.
But that's a different thing. I am not talking about that thing. Header star L is still valid, but L will now be a pointer to a pointer of node pointer to a node pointer. Okay, such data structures may be used, but here I didn't intend to use such a type. I just wanted a node pointer to be called as L. Okay. Header star L still makes sense in other contexts, but this is not the context we are talking about. Okay. Now let us see how I can actually modify a list from inside a function and still I can handle it from main. Okay. So what I will do, insert at the beginning. This function I will write. Then what I will actually, after a small break, what I will do, I will write a code for a sorted linked list where we will do sorted insertion and deletion also. Anyway, insert at the beginning. So what I will do, okay, instead of header, I will just write node pointer. Insert node pointer, something like H, L, whatever you call. And what do I want to insert? Maybe that is X. Okay, this code I have to write. But before doing so, let us see what are the possibilities. What are the cases? So H is null itself, which essentially stands for the empty list. There are no nodes. Okay. So if this is the input, then after this, okay, I will create a node, make it this next pointer null. I will insert X as the data field, and I will return a pointer to that node. Okay. So whenever you call it from main, you can say L equal to insert X, insert LX. Okay, so I will look at the main later. Next one is case 2. H is not null. Okay, so H already contains some things. L is containing one or more elements. Something like this. And maybe U stored here, V stored here, W stored here, Z stored here. Then what I will do, like this, I will create a new node. I will let this point to this, and I will return this. So, if you look at the main, you will see that now the list looks like this. Starting from here, X is included. Then U, V, W, Z, whatever the previous thing was, that will be there. Okay. Yes or no?
So can you show the previous page once?
Previously, I have not written anything. I am passing this header pointer and the new value X that I want to insert, and I am inserting. I am returning again a node pointer. Or you may call it. Okay. Okay. So there is one thing common. That common thing is you create a node, stored X there, return the pointer to this node, and the next pointer of this will point to the earlier header. It's here. Here also the earlier header was null, so this null pointer will point to the earlier header. Okay. So, irrespective of whether it is we are in case 1 or we are in case 2, the code for insert at the beginning is more or less the same. So what I will use, node star P. Okay. Then what I will do, P equal to node star malloc. Now this is a single element array, so one star makes no sense. I'll just say size of node. P's data will be X. P's next will be the old header H, and then I simply say return P. Happy or not? So this is a malloc. I am just asking for size of node, this much memory. Of course,
So
here
here H is the one. H is the node after P.
H is this.
So H is the node directly after P.
Yes, insert at the beginning means this new field will be this new structure will be there, and its next pointer will point to the old header. Okay.
Yes, sir.
Okay, so how do I call this from main? Let us also see the main.
So can you explain the case of null hits?
Node pointer header. You may call it by any other name, maybe L equal to null. This is just to indicate that currently it's pointing to a to an empty list. Then I have int I. Maybe for I 0 to 9. what I will do, L will be insert L, maybe I square. Happy or not? So L is a pointer, so it can be a valid L value, left value. Okay, insert it, and that function returns a pointer to the new beginning of that to the structure, which is the new header. I will which is the new first node, and I'm assigning L equal to that. Okay, and then I can simply say traversal. Happy or not?
Yes, sir.
Okay, so this is how the header may change. The function returns.
So what is it is a function.
Huh?
So traverse.
No, I didn't hear you. What was the query?
Sir, traverse is a function here.
Can somebody explain what he's saying? Oh, you want
Sir,
to see
he
the
is
function?
asking if traverse is a function or not.
Traverse is a function, this function. I have already written it, right? It simply prints the things one by one, starting from the beginning to the end. Okay, it's this function. Okay. Maybe before a break, I will just write another function. Then after I come back, we will look at sorted insertion. So what about insert at the end? So far we have seen insert at the beginning. So what about insert at the end? Okay. Okay. This is slightly more complicated. So I will write a function called append, which is essentially insert at the end. Okay. So now these two things are different. Case one, the input H is null. Then this is basically the same as insert at the end and insert at the beginning. Okay. So I will just create a new node, store the key X there, make this null, and return this pointer. Because if the input list is null or empty, then insert at the end and insert at the beginning are essentially the same thing. Otherwise, H is not null. So it is something like this. Okay, maybe something like this. Then if I want to insert a new thing, what would happen? Okay, I will use a different color to notice the changes, to indicate the changes. New node should be created. This will be null. And this pointer from null, it will change to a pointer to this. And as a header, I will return this pointer. Happy or not? This is how the structure will change.
Yes.
Okay. So let us write this function. Okay, append. It will return the new node pointer. Start with the new header H, and you want to insert, let's say, X. First of all, I should not change H, because I may have to return this old header in the case when H is not null. Okay. So, sorry, not int, node star p. I will use two pointers. Y, that will be evident later. First of all, let me allocate memory to this. In either of these cases, I have to create one cell, right? Like this or like this. Okay, one thing I forgot. Okay, maybe after this I will just do it. Malloc, size of node, p data will be x, p next will be null. This is true in all the cases where h is null or not. But if h is null, there is nothing more to do other than returning that pointer. Okay. So if h is null, or you can see if not h, return p. Happy or not? Case 1 is handled, right? Happy or not? Tell.
Yes, sir.
This is case
Yes,
1.
sir.
Okay. If h is not null, eventually I have to locate this node. And then I will modify the next pointer to point to the new node created. Okay, for that I am using that pointer q. Okay, so q equal to h. I'm starting from the header. Okay. Of course, if I say while q not equal to null, then eventually q becomes null, so that's useless. So while q next not equal to null or something like this, not equal to null, I do not need to write. Q equal to q next. So this loop breaks when q next becomes null, that is q is pointing to the last node in the list. Happy or not? It is not while q next.
Yes, sir.
Okay. Then what I will say, q next, which was earlier null, this will point to p. It was q next was null, so eventually q comes here. So I change q next to this. This is already made null, and return the old header h.
Sir,
Ah,
what is the use of returning h if we are not changing it?
I do not know which case I am. Okay, if h is null, I am changing it. If h is not null, I am not changing it, but this is a function that works
Okay,
in
okay.
all situations. In fact,
Okay, for null we need to return a pointer. Okay.
okay, if you look at this main function, instead of this insert, I could have used append. Or sometimes append, sometimes insert, something like that. And the code will work exactly the way it worked for insert. Happy or not?
Yes, sir.
Yes, sir.
Okay. Okay.
Yes, sir.
Okay. So this is actually, this illustrates, where is that? Yeah. So this illustrates locating a pointer to the last node. This loop does it.
Excuse me, sir.
Tell.
So we could have done this in main and changed the
Ah,
pointer pointing to last.
we could have done it in the main, but the idea is that we can also write functions and
Okay, sir.
can modify linked list by returning the new header. The new header may be the same as the old header. The new header may be different from the old header. So whichever the case is, the new header is returned. So if you assign that thing to your header variable like L, you are done. So this is a standard way of doing things. In fact, in this insert at the beginning thing, this header is always changing. Here, the header is changing only when the list is empty. Otherwise, it remains the same. And after the break, we will see an example where the header may change or may not change, and that is basically conditional. Okay. 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 So that's about simpler things. Next thing that we will start, next time I will just write a code that is sorted insert. Okay. So its idea is something like this: 15, 32, 48, let's say 57. And I want to insert, let's say, several things. If I want to insert 8, this is similar to insert at the beginning. If I insert, let's say, 63, it is similar to insert at the end. And if I want to insert 45, it is an insertion in any arbitrary point. Okay. So how we can in general do it? Okay. So for the rest of today's class, I will just write a code for this sorted insertion plus this traversal and all that stuff. Okay. We will see. So let us have a small break, 5 minutes, 7 minutes, something like that. I will come back. Okay. Okay. So.
Hello, sir.
Yeah, tell.
Yes, sir, I thought you were muted.
I was muted. I will come back. So this is a 5 minutes
Oh,
break.
okay, sir.
After this, I will come back.
Yes.
Okay. So hello, I am back. Okay, so let me now write a code illustrating all these concepts and little bit more.
Show the page where you wrote append. Can you show the page where you wrote append function?
Which function? This one maybe?
Yes. 1 second. Yes, sir. Thank you.
Okay. Okay, so let me now start writing a code. Sorted list. Maybe I will use this rand function with time. So, srand unsigned int time null. Okay. Here, let me use this type definition, struct underscore node. I have data and I have a self-referencing pointer, struct underscore node star next. And I am calling it node. Okay. So let me write down the traverse function first.
Sir, while type defining, underscore is mandatory.
No. Some name you give. And I think struct node and
underscore, sir.
I do not know whether this underscore. You give some name. Struct node 123, struct node 1, anything, any valid node. Only thing I believe that struct underscore it should not be called struct node because this is node. Possibly this is not allowed by the compiler.
Yes, sir, it's not allowed.
Okay, having node and struct node both. Okay, that is the reason I have to give some new name. Okay, so let me just write down this while p %d p data p equal to p next. Now maybe just after this I will just print a line break. Okay. Okay. So now.
Sir, what is srand and time null?
Forget it. This has nothing to do with pointers. This is seeding the random number generator with the current time. So that on different inputs I will get different values. Anyway, don't worry. I will again call it insert. This is now sorted insert. This is the header. And now I want to insert X. Okay. I have to use multiple pointers. Not pointer P, Q, maybe that's all I need. Let us see. First of all, I allocate memory to P. Size of node. P data equal to X. For the moment, I am not okay. Okay, maybe I do it. P next equal to null. Now, if it is an empty list, I simply return P. Otherwise, I will have to.
Sir, return type of insert is void, then we need to change it.
Void starts.
Node star. Node star is better. White star is okay, but node star is better. Yeah, we will do it. Node star. Yeah, no, that's a mistake. If age is null, just return this P. Otherwise, we need to locate, we need to have the correct insertion position. So you once again look at this. If it is 8, okay, the insertion position is here at the beginning. If it is 63, the insertion position is here at the end. And if it is something like 45, the insertion position is here. Okay, not this. Okay. Okay. So first what I will do, I have handled one case, then I will handle this case. The thing that I want to insert is the smallest element. Okay. No. Where should I go? Here. Okay. So this is case 1. I will just write a small thing. Case 1, input list is empty. And this will be a new element and I will just do it. Then case 2, X is smaller than all list elements. So this implies insert at the beginning. Happy or not? Okay. So this case is also not difficult. We have seen that we have already allocated memory to P. So I will let P next be the old header and I will return P. In fact, case 1 and case 2 are similar because in both the cases I am returning P and P next is pointing to null here and here H. But anyway, this is okay. Okay. Case 3. Insert. Not at the
Sir, we have to check
condition
now.
in second case.
Huh? What?
If H data less than, if H data is greater than P data, you don't
Yes.
need to write that statement.
Yes. Yeah, without that, how can I? I cannot do it blindly. Yes, correct. If X is less than H data, then P next equal to H, return P. Otherwise, I have to locate the node after which I will make the insertion. Okay. So the first thing is
So it is returning basically the first node, like the first node it is returning. whichever header is supposed to point to after the insertion, right?
Yes. That may be the new node pointer. It may be the old header also. Here, of course, I will return H. So H is not empty and it is not at insert, is not at the beginning. So I will first locate the node after which the insertion is made. Okay. So for that, I will again use this Q.
Yes, sir.
H. Okay. Let us look at the picture. Okay. So if it is 45, I will come here. If it is 63, I will come here. So I will start Q. Okay. And since 15 is smaller than 45, I will move on. 32 is smaller than 45, I will move on. And then 48 is not smaller than 45, so I will stop here. Whereas in this case, maybe I use another ink, 63 here, come here, come here. This is 15 is 63 is larger, 63 is larger than 32, 63 is larger than 48, 63 is larger than 57. Then the loop breaks, not because something like 45 less than 48 will happen, but because the loop, because the list ends. Okay. So what I will do, while Q next not equal to null, and then X is greater than this is correct, right? So there may be two reasons why this loop is broken. The case of 45 is the second reason. X is greater than Q data. X is less than equal to Q data. No, am I making a mistake? I think I am making a mistake. Q data 1545. There is a
So
mistake.
shouldn't
Sir,
be
I
why
must be
Q not equal to
X.
null?
Huh?
Why Q not equal to null? Shouldn't we write that? I mean, I have.
While Q not equal to null, no. So if Q becomes null and the loop breaks because of that, then I am in trouble.
Sir, I think it is X greater than Q next data.
X greater than
And Q arrow next arrow data.
Q next data, then I am starting search from 32, not from 15. There are many ways I can handle this.
Q next set pointing to data.
Uh, no, the problem is that if the insertion is here, okay, Q next data. Oh, Q next data will solve it. Let us see. Okay. Insert at the beginning is already handled. Maybe if there are equality equal to, let's say equal to. There is another possibility. If something is already there, I will not insert it, but let's say I will allow duplicate insertion. Okay, doesn't matter. So it already means if this condition is satisfied, this means x is already greater than age data. Yes. This is fine, right? Because
Yes,
this
sir. Means earlier it pointed
Yes, sir.
at earlier Q pointed at some 45, and then now it points just before it.
Yeah, because this condition x less than equal to age data, this is already handled as a separate specific case. So I
Yes,
will
sir. Otherwise,
yes. Okay, fine. Well, that is the reason I have this special case. Okay, now fine. Q next not equal to null, and therefore I can access Q next data, making Q next. Okay. So now the loop may break because of two reasons. Q next may become null. Okay. So I have in this case like 63. I want to insert a very large element, larger than all the elements. Then Q is pointing here. Another thing is that x is less than equal to Q next data. So 45 is less than equal to this next data 48. Okay. It turns out that these two cases are essentially similar. What I have to do here is that P next, sorry, will point to Q next. So this P next will point to, this is Q next, or here P next will point to Q next, null. And Q next will be P. And finally I will return the original header H. Happy or not?
Yes, sir.
Okay, P next.
Sir, I did not understand the third case, sir. Can you explain?
No. So this condition is not satisfied, so I already know x is greater than the first data. Okay, so it's like 45 greater than 15 or 63 greater than 15. So then I will sit at this node and look at this next one. If this is small, as in the case of 45 versus 32, this is small, I will move from Q to Q, this yellow pointers. Then I will look at this next data. Okay, this time I see that 48 is bigger. Currently I am pointing to a node which is essentially by induction storing a value less than this, and this is storing a value greater than equal to this. So this is the insert position. Another possibility is that if I want to insert a very large value like 63, then next one 32 smaller, next one 48 smaller, next one 57 smaller, and then there is no next one. So I know that there will be an insertion at the end. This is the append case. Okay. So if it is the insertion of 45, it is something like this. If it is the insertion of 63, it is something like this. Okay. So after this, what will happen? Okay, where is my pen? Yeah. Essentially, this will change to this, and this will change to this. Or if it is in this case, this will change to this and this will change to null. Actually it is null, but it is same as this. Okay. The idea is that you should not cut the list here first, because then this address is lost. Okay. So first let this pointer point to this old address. So this P next becomes same as Q next. Okay. So at that point, this pointer and this pointer, they are both pointing to this node, but then since you have copied this address here, you can now safely cut this pointer and let it point to this. Okay.
Understood, sir.
Okay. So now Q next will be P. Q next will be P. And in this case, you are returning the original here. Okay. So I have all the node pointer list. So initialize it to null. You could have initialized it here also. And how many elements you want to insert? Maybe something between 10 and 20. Okay, and I'll do it randomly. Maybe I will have another integer x. While n okay, while n minus minus maybe. Okay. Again, let's say I will.
Excuse me, sir.
Yeah.
So
Well,
in function, in the last line, sir, there should be, I think, Q equal to P, I guess. Because Q dot next equal to P will point to the uh, different address. Means
what is this? This is Q.
so Q
This
dot
is
next is again going to 48. At 48 is
earlier Q
address.
next was 48. Now P next will be 48, and then Q next will be P. This is just including this node. Yes
Okay,
or no?
sir, got it. Sir. Good.
Okay.
Yes, sir. Yes, sir. Yes, sir.
While n minus minus x equal to rand percent x, I will just print insert percent d or maybe percent 2d colon x. Then what I will do, I will actually call this function and I will store L equal to insert L x. Then I will just call the traverse function traverse L. Okay, maybe before this I will also traverse L. Maybe exit 0, and maybe I also write n. Okay. Okay, so I am initializing L and I am randomly picking how many inserts I would like to make, something between 10 and 20. Then I am one by one making these insertions, 10 insertions with again random values, rand percent 100. I will insert, and maybe here also I write percent 2d traverse function so that it looks neat. Okay, compile with warn all.
Sir, in the place of %2d, you wrote 2%d.
That is the problem. But what happened to this rand? Did I make any mistake there? Rand percent 100 is not a problem.
Might be rand into 11.
It should be rand %11.
That was 11.
So did I include s2delete.h is there? What is the problem? One x equal to rand percent 100. So what is wrong about it? Too many arguments to function rand.
So rand 11 means
Rand 11.
yeah,
Sir, rand
n
percent
square.
11. Right?
Just multiplied.
Oh. Okay. The problem is here. Okay. Percent 11. Sorry. Stupid error. Okay. Let's see. Maybe n first. Maybe this is first. Okay, let's see. 15 inserts I will make. Initially L is empty. Inserting 26, it's like this. 94, so insert at the end. It is like this. 98, once again this is like insert at the end. Then again 26, so this is like insert at the beginning, right? I have less than equal to here. Less than equal to here. Okay, so insert at the beginning. Insert 0, again insert at the beginning. Then 86, it is between this and this. So 86 is inserted here. 30, it is between 26 and 86. 26 and 86, 30 is inserted. And this is okay. 0, 1, 26, 20, 30, 31, 31, 51. Happy, right? It's working.
Yes, sir.
14 inserts, okay. And if I want to make slightly larger lists, maybe up to 25. Okay. This is sorted, right? Yes. Okay. Happy or not? So the idea is understanding this general insert function. There are other insert functions also, like insert at position I, specify some position I. Okay. So this is sorted insert. And I do not want to write the delete functions today because it's already much for today, but I will just illustrate. Void reverse print here. I am using H, right? Let me use H. So this traversal is essentially printing in the forward direction. If I want to print in the reverse direction, what should I do? So I am doing something like this. Okay. Otherwise, I will make a recursive call. After this call returns, I will print okay. So maybe I will do this thing also. Alongside this, reverse of L is there is something wrong. Okay, I should return, right? Otherwise, how will it work? Then make a recursive call, and after it the call returns, you print the data. Okay. No, this is not the correct place where I should have the printed. Forget this thing here. Here I have a print. That's the problem. Okay. I will just something like this. Let's see. Just that this looks nice. Okay. So are you happy with this recursive function?
Yes, sir.
If it is null, nothing to print, return. Otherwise, print the remaining elements, and when this returns, you print the current element. That's precisely what it is doing. So 90, 81, 72, 64, 56, 49, and so on. Okay. Okay. So maybe I stop here because the delete thing I will take up to tomorrow. It's not difficult, but maybe let us leave it for tomorrow. I just wanted to do one thing. So let us look at this insert function. So node star P, you are allocating memory, setting its data, returning it. Now I will just write it in a little different way. This is what I have been keeping on forgetting. Maybe it's the same thing. Node star, insert, node star H, index. Instead of node star P, I will just say node N. N dot data will be X. N dot next will be H. Do you understand the difference? Instead of mallocing, I am using a node, setting its data to X, next to this earlier header H, and I am just returning a pointer to N. Does this program have a problem or not?
So it should be a static node, I think.
It is a static.
Address of local variable should not be written.
This is address of a local variable. So after this function returns, this node N does no longer exist. It no longer exists, and its address is essentially useless because this address may be used by some other thing. Okay, and so this is the idea. This is what I wanted to do. This is not what you should do, because this is address of a local variable. And as soon as the function returns, this local variable will not stay. Whereas the good thing about this is that this memory will stay after the function returns. Will stay. So this is not the correct way of doing it. This is the correct way of doing it. Okay, so yeah. So that's one thing I was skipping on forgetting to mention, but this is an interesting and important thing. Okay, so yeah, it's just 5. I could have taken another 10 minutes, but let's stop today, because I believe this is already heavy material for you. Yeah, so you tell if you have any specific questions.
So can you please share this
So
code
you
on the
will
website?
upload. Yes, sir. Same thing. Code.
What? What?
So can you please upload this code on the website?
This one?
Yes, sir. Today one.
Yeah, this I always keep on doing, right? Website means you go to my section.
Yes, sir.
Yes, sir.
Okay. So
Yes,
you
sir.
click here. This is the PDS page of this semester. Click here, and all the sample codes are uploaded here. Okay. So you can do it this way. Okay. So something like sortedlist.c will come today after the class. Okay. Yeah, tell.
Sir, I have a question. Can we pass pointer to a recursive function?
Why not? This is
Sir,
what we have done
I
here.
tried to use Fibonacci sequence using pointers.
And then what happened?
It did not print. It did not print, sir. Nothing it printed.
It depends on what you did. Technically, you can pass pointers as you see here. You can even return pointers.
Sir, in recursive call, what we will write?
Huh?
P or star P. In recursive call, what we will write in the function input?
Look at this function. That is why I have written this function. It's node pointer 8, and I am passing the next pointer to this node h next, that is star h dot next, that is I am passing to this ref print function. So after all the other things are printed, this will come back and will print age data. Now, what is the question? So I'm doing it here. Then that is the reason I have shown you this recursive function. You can pass pointers, no problem. Yeah, any other question? So there are lots of things you can do. I have just shown linked list reverse printing. How about linked list reversal? So something which is pointing to like this will point to this. You will get a pointer here, and this will be empty. And let's say doubly linked lists. Okay, maybe tomorrow, depending upon how much time I get, the first thing I will do is deletion in a linked list. Maybe this sorted linked list, and then a few other applications like linked list reversal, working with doubly linked list. Okay, it depends how much time tomorrow we will get. We will look at this. Yeah. Yeah, anything else for today?
Sir, I had a doubt in the previous class theory which you taught.
Previous?
In previous class, you gave a question in which you wrote int star star a30. So, sir, when I checked, it was a pointer to a pointer. So, my doubt is that is star operator different from star star operator? Or that was my doubt.
You think about it. Why I should answer every question? It's basically an array of 30 pointers of type int star star.
But sir, when I checked with the size of operator, it returned size of a pointer variable, not size of 30 pointer to pointers. So that was doubt.
How is it possible? Maybe just a minute. I am. Star star P30. Okay. It should be a two-dimensional array, right? That should be the case. Yeah, 30 pointers, 8 to 40.
Okay, sir. I think I made a mistake or something different in my compiler, but I don't know. Okay, sir.
It's an array of 30 pointers, and each pointer is of type int star star.
Okay, sir.
Okay, maybe this thing I just did it. Yeah. So, any other question? Yeah, if not, let us stop today's session.